Oh, hi. Hang on just a minute. Okay, so our last lecture was about RGB color theory. Red, green, and blue being the components of light. Everything we see, be it from a computer monitor, be it looking in an apple, whatever. Everything that we see is a combination of red, green, and blue light. And the color that we see depends upon how much of each of those three components is there. Today, we're going to extend that to talk more about printing and how printing works. This lecture is going to have a little bit of unlearning. I'm going to cover a lot of the misconceptions that we have about the way that printing works. The first of those misconceptions is, what are the primary colors? Now, we learned that the primary colors are red, blue, and yellow. This is something that we learned in kindergarten. I learned it in kindergarten, and I would like to call those the artist primaries. But we know that that's not what we use in a computer monitor. We saw on the screen that pixels were red, green, and blue rather than red, yellow, and blue. And we know that we don't print with these primaries, so what's up with that? I've devised an experiment here to help us test out what the real set of primaries are. This is described on my blog. I have the link to it here. You can get to that from Canvas. Along the top here, we have the CMY primaries. Along the middle, RG and B primaries. And along the bottom, we said we have red, blue, and yellow primaries. That's the first sheet. Now, when you do this experiment, you would print that, put that back in your printer, and print it again. And let's see, you've got you can flip it this way, or the piece of paper, when you put it back in, you can put it this way or this way, and this way or this way. So there's 4 different ways that you can do it. Usually it takes me about 8 tries before I get the right one to get things to line up, because I want this second page, I want that to print on top of the first page. And you see here that along the top row again we have cyan, magenta, and yellow, only this time they're turned 90 degrees from the other. And we have red, green, and blue, and we have the blue, yellow, and red, or red, yellow, blue, red, blue, green, So we have the 3 sets of primaries there, and with this we can print one on top of another. And this is what I got when I did that. Here's what we get if we look at just the artist primaries. So we have across the top red, blue, and yellow, and across the bottom we have blue, yellow, and red, all turned 90 degrees. So when we look at this particular square, we should see a combination of red and yellow. This one we should see a combination of blue and yellow. And the one here on the left, we get a combination of red and blue. And we see what happens when we overprint red over blue, all those different combinations. And there we see, let me move out of the way. Here we see what we get with those combinations. The red and blue, we mix them together, and let's see, my kindergarten teacher told me that that's supposed to be purple, and I am not seeing purple. And when we print blue and yellow together, we get green. Yeah, it's kind of a wimpy green, but it is green. Okay, I'll buy that. And I wouldn't pay money for it, but I'll buy it. Yellow and red printed on top of each other. We get an orange, which is a fairly decent orange, not so bad. So this combination really does not work at all according to what I was taught in kindergarten. These primaries, red, blue, and yellow, were conceived of first by a lithographer, a guy who did printing, by the name of Jacob Christophe Leblanc. He was trying to make accurate color for anatomical printing, printing of inside of dissections and stuff like that, okay? So a little weird, but He wanted to get accurate color, and he started off with a large number of primaries. He'd make a woodcut for each one and print on top of and top of and top of. And he said, there's got to be a better way. So we started the idea of trying to reduce that to a minimal set of pigments. And he found red, blue, and yellow were a very good combination, or more or less kind of. Let's see what we get when we combine the monitor primaries, red, green, and blue, the primaries that we find on a computer monitor if we look at the pixels with a microscope. This is what the overprints look like. We've got here the combination of red and green, which on a monitor we see yellow, if I remember right. That was the weird one. Red and green make yellow, yes. And no, that's not yellow. That's brown, and it's a muddy, icky brown too. Who wants that? Then we mix the green and the blue, which are two primaries that should give us cyan. Yeah, cyan. They're supposed to give us cyan on a computer monitor, but here we see when we mix them in a printer, we get I don't know. It's a dark green. Army green, maybe I'll call that, or emerald green. It's not cyan. It's not nearly bright enough, which kind of makes sense because when we're printing one thing on top of another, we're taking out color. So that would make it darker. And similarly, when we mix red and blue together, we get, what was that one? That one was supposed to be magenta, if I remember right. And, oh boy, that is the weakest example of magenta that I can imagine. I'm going to call that dark gray. I'm sorry, but the monitor primaries, red, blue, and green, red, green, and blue, we cannot use those for printing. They suck. So red, yellow, blue don't work well for printing. RGB don't work so well either because those are additive primaries. They assume that you're adding, but when you print, you're taking away light. So we want subtract. What are the primaries that we should use? Here we have the printing primaries, cyan, magenta, and yellow, and we see the results from that. Cyan mixed with magenta gives us cyan, magenta. Cyan takes out I got to go through this in my head here. I'm sorry. Cyan and magenta. Cyan takes out red, and magenta takes out green. So red and green are gone. We should be left with blue. So the result that we see down here is, well, it should be blue, but it's not quite blue. It's kind of a purple. That's because the printing inks that we actually use are not perfect. The filters that we used in class, those were pretty close to being perfect, and we got a good blue out of those. But printing ink, just a matter of practicality, cost, largely. The cyan ink isn't as good as it should be, so we get blue, or purplish blue. Now, we mix magenta and yellow, we should get red, and, well, we get kind of an orangish red. Same reasons. We don't have perfect inks. Yellow is really a good ink. I mean, it gives you a very rich color, a very rich yellow color. Just reflecting the, which one's, red and green. Yes, it reflects the red light, the green light, and it absorbs a lot of the blue light. It's a really, really good ink. But magenta is not so much, not quite what we want, and we get a slightly orangish red. Finally, we look at the green, and yeah, okay, when we mix yellow and cyan, we get a fairly decent green. So here's my set of combinations. This is what printed on my printer, and I think for my money, these are the ones that we want to use. We want to use cyan, magenta, and yellow when we print because that will give us the widest range of colors, the largest printing gamut. I had a student do a project for me once. She was a painter, so she really got into this. She collected as many different colors of paint that she possibly could. And she came up with the CMY gamut with paint. She painted with cyan, magenta, and yellow ink, and she mixed them to get different colors. And here we see the range. That's the green dots, which are out here and out here. This is in C-Lab space. This is an A star, B star plot. Basically, what we need to know is that the further out we get from the center, the richer the colors are, which is good for getting gamut. We get rich colors. She also did this with the RBY or RYB gamut, the artist primaries. And in this part of the color range where we're dealing with orange and red, yellow is up here, magenta is down here, so all the colors, mixtures of those are in between here. We see that the CMY gamut is better. But then over on this side, we see that the RYB gamut is better. So in terms of paint, you mix. Depends on what part of the gamut you're in as to what set of primaries you want to use. That leads me to ponder that maybe all this talk about primaries, that there are these specific primaries, maybe that's kind of another one of those lies that isn't quite all the way true. It's kind of true that you can use all those primaries that you could use, for example, CMY to give you all the, but you know, there's still some, it's almost like depending upon the color, you want a different set of primaries. If you want to get good color in this range, you want to get your purples, then maybe this is a set of primaries. So I'm beginning to doubt the whole premise behind primaries. The part of the premise of primaries is that you can get all colors by mixing together the primaries. And I'm wondering if maybe that premise isn't quite right. You can get a lot of colors, but there's colors, no matter what set of primaries you use, you're going to miss some of the colors. I think that's true. And here's another thing that's true. When you're talking about printing, the best set of primaries that you can find is cyan, magenta, and yellow. So that's what we're going to be dealing with. Why the lies? I don't think that my kindergarten teacher was really mean. I mean, she was a really nice lady, really, I think. So, you know, she didn't intentionally mislead me about what the primary colors were, but why the lies? I have one possible explanation. Let me rough this out a little bit. If you go into the press room, and here I'm talking, this is offset printing, so this is fairly thick ink. This stuff is like honey. Here we have magenta, cyan, yellow, and black ink. That doesn't look like magenta to me. In the bucket, that looks a whole lot like red. And in the bucket, if you look at the cyan ink, it looks blue. I mean dark blue, navy blue, not light blue like cyan is. So maybe part of the reason you go into the press room and they refer to them as red, blue, yellow, and black, which, you know, as a color scientist, that just annoys the heck out of me. But the thing is that that's the color that they look like when you look at them in bulk. It's only when you put down a tiny layer, and that layer is about a couple of microns thick. I mean, we're talking thousandths of a millimeter thick, that much ink, that little ink, I should say. Magenta ink will look magenta rather than red, and cyan ink will look cyan instead of navy blue. And as you may guess, I did a blog post about that. Here's another explanation for why we may have the set of primaries, red, yellow, and blue. Cyan and magenta, let's say they're the true primaries, and I don't see them on this list. This is the list of the basic color terms that we got from, who was that? Berlin and Kay. Yeah, back in the 1960s or 70s. They did not come up with that as one of the basic color terms. So cyan and magenta, outside of this little world that we live in, the graphic arts, those words are not very commonly used. So maybe that's another reason why it's just simple. When we're teaching this to somebody, when we're communicating about the primary colors, maybe Jacob LeBlanc, maybe whatever his name is, Jacob LeBlanc, the lithographer, maybe the inks that he came up with I'm sorry. Yeah, the inks. He used inks. I'm sorry. The inks that he came up with, maybe they were actually cyan and magenta, and he called them blue and red. This image here shows another misconception that we have about ink and paint. We like to think that they're, kind of the same thing. But imagine, let's say I were to want to paint this room, and I would, it's kind of a sage green right now, and let's say that I wanted to make it a happier color, a yellow color. I go to the paint store, I buy some paint, I find the cheapest paint that I can find because on my salary, I can't afford expensive paint. So I get the cheap paint, I come back here, I paint the wall. And what happens? I can still see the sage green coming through. That's not a good thing. I don't want that to happen when I'm painting. Paint we want to cover. We want it to be opaque. We want it to hide what's underneath. This is paint on this side. On the left-hand side, we see what happens if we take this sheet of paper that has a black mark on it, a black box. I paint over it. That's what I want. I don't want the black box to show at all. But ink, I want it to show. I want it to be just the opposite. I'll explain that in just a minute here. Let me move on to misconception number 3 about cyan ink, or ink in general. We would like to think that cyan ink, cyan light is a combination of blue and green, so we would like to think that cyan ink is reflecting the other two, the blue and green, and that it's absorbing red. That would make sense. And similarly, we would think that magenta is absorbing green and reflecting the red and blue, and that yellow is going to reflect the red and the green. But that's not quite the case. These two images here are a simulation of printing. I took one of those yellow acetate filters that we showed in class, and I put it on top of a yellow sheet of paper. And then I took the cyan one and I put that one on top of a different piece of paper. And we see that it kind of acts like ink. It's like this is a layer of ink that I'm placing down on the white piece of paper. That's basically what ink is. Recalling our Star of David diagram here, if I mix cyan ink and yellow ink, I would expect to get green. And we see that that is indeed the case, that when I mixed those two together, I did indeed get green. So this is behaving a lot like ink. The acetate filters act much in the same way as ink does. And if I take all 3 of those acetate filters and combine them together, I see that I can get cyan, I can get magenta, I get the combination here, which is a blue, well, it's kind of purplish blue. We see a nice red, better than I get with printing ink normally. I get a nice green when I mix the cyan and yellow together. So there I see the proof that these acetate filters are a reasonable approximation, a reasonable simulation of what happens with printing ink. What if I had used paint instead of these acetate filters? I would get cyan, I would get magenta, I would get yellow, and depending upon the order that I put them down, one would cover the other, and those are the colors that I would see. The fact that the transparencies, the acetate filters are transparent, the fact that they are transparent allows me to create those secondary colors. We would think of cyan, magenta, and yellow as being the primaries. The secondaries are the combinations of them. Because of that, I can create red, green, and blue, and that allows me to expand my gamut. I also get, if you look in the center where there are all 3 overlapping, I get black. So the fact that ink is transparent and paint is not is a very critical fact. From a theoretical standpoint, this is what we have. This is our model of cyan ink. Here's a blob of cyan ink laid on top of paper. Dimensions are a little distorted here. We get red light that comes in, it hits the cyan ink, and the cyan ink gobbles it up. It absorbs it. We take a look at the green light goes through it. The cyan filters, like as ink is, will pass the green light. It will also pass the blue light. And the key thing here that's kind of interesting is that the light is reflecting from the paper. It's not reflecting from the ink itself. So to say that cyan ink reflects blue and green is, kind of right. I mean, cyan ink on top of paper does reflect those two colors, but it's actually the paper that's doing the reflecting. And the cyan ink, its job is to absorb the red. Yeah, you got me on a technicality, right? That's a silly thing. I mean, who cares if it's the paper or if it's the ink? It doesn't really matter. Well, it does kind of matter in that the paper is an important ingredient in this whole thing. The color of the paper. Let's just say that we had paper that was a different color. Rather than white, let's say that it, let's say it absorbed green. If it was magenta paper, I wouldn't get the same color when I print magenta, when I print cyan ink on top of it. So we need to, I'm bringing out this excruciating detail on this, but it's really important that we consider that paper is part of the equation. It's the fifth color that we print with. So returning to the myth, cyan ink reflects cyan light? No. It's the paper that does the reflecting. Cyan ink does not reflect green and blue. Paper reflects red, green, and blue, and the role of the cyan is to absorb the red. With that as background, it makes it easy for us to say why it is that ink has to be transparent, so we can get more colors. Moving on to myth number 4. Printing an image is easy. Well, yeah, you probably weren't expecting that would be the case, since we have actually a whole school devoted to figuring out how to do printing. We have 8 colors that we can make, right? We've described how to make cyan, magenta, and yellow, and how we can mix those and get red, green, and blue. And then we can make white by leaving off the color, and we can make black by putting them all down. So there's the 8 colors that we have. So here's an idea about how we would do printing. This is what the software would have to do. For each pixel in the image that we're looking at, we would find the closest of all of those colors. We'd find the color that is closest to that particular pixel, and we'd put that on the page where that image was. So if this is the image that I start off with, a beautiful picture of a garden, the way that we would print that is like this. Now we see we've got kind of all the same colors, but this is we would call this posterization. It is not it's a nice effect, but it's not probably what we want to put into the Lawn and Garden Club newsletter. The way we do this in printing, instead of doing what I suggested, we do halftoning. We can't on our printing press say, at this point I'm going to put this thickness, and over here I'm going to put a little bit more ink down, and over here I'll put a bit more. It's hard for us to make a printing press that does that. Mechanically, it's a very difficult thing to do. But what we can do is we can say, we'll put ink here and not here, and we'll make the dots, the size of those dots vary with the color that we're trying to put down, the richness of the cyan, the richness of the magenta. We'll adjust the size of those dots, and we'll make those dots so tiny that you can't see them, or at least not notice them. Make them so tiny that I can get the appearance of a gradient here. On the white end, we have either no dots or little itty bitty tiny dots. They get bigger and bigger as you move over here. And at the far end, you can see that the dots have all merged together to create black. And with this, I show here with a black ink how we can get all of the gradations in between. And it's such a beautiful illusion. To illustrate this process, I start here with an image of my puppy. This was Scrabble. He's not with us anymore, but we have Mozart. You'll see pictures of him later, I'm sure. But this is Scrabble. If we halftone Scrabble, we see a little bit better here. We can see there's all kinds of dots, but let me zoom in on that so we can see a little bit better. There we see a very sharp close-up, and we can see individual black dots and magenta and cyan and yellow dots. Over here where it's lightly colored, we see tiny dots. And over here where it's dark in the eye region, we see that the dots are very big and overlapping. That's how we get through this halftoning, we get this. And we see that there is a pattern to that. We call these little things rosettes. There we see a higher magnification version of it where the dots are very clear. This is what we call the color separation process in printing. We start off with this image here, and the software will create a cyan plate or a cyan image that is just the areas where we need to have cyan. So in this image over here with the sunflowers, everything is yellow and green. All the yellow areas are white. There's no cyan needed to make those colors. But in order to make the green and the dark colors here, we see that that leaf right there is almost solid cyan. That's how we create the cyan plate. Moving on, we have the magenta plate, the same sort of thing. Here we see very dominant. These orange flowers require a lot of magenta to make the orange color that we want. And moving on to the yellow image, we see that this part of the image where we have the sunflowers, almost the entire image is solid yellow. That's something I've seen a lot on yellow plates, is that there's just almost solid coverage. And there we have the black. The black is filling in. It helps to make things a little darker. We'll talk more about that later, about why black is needed. Theoretically, we should be able to get along with just cyan, magenta, and yellow, but black is a key part of it as well. I want to introduce another concept here, one that maybe isn't necessary right now, but it will help us as we move forward in this. I'm going to talk about a color space, and in this case the red, green, blue color space. This is the color picker that we have in Microsoft products. Red, green, and blue, each individual amount. We can adjust each one of those to get a whole bunch of different colors. And this is what it looks like three-dimensionally. We start off this cube. Think of this as a space. We have black here, and as I add red, if I adjust this number here, the 0 that's for red, I'm going to move it in this direction. So that's a position in this cube. And if I add green from that black, I move up in this direction. If I add blue, I move backward. And all of the different combinations are there. Hang on just a minute. I made one of these. And just a moment here, I'm trying to, yep. Okay, so here is what that cube looks like. We have, let's see here, we have white at this point. There's the white end. And this particular face here, we have yellow moving along the bottom. We have red moving up to the top. And over here, it's actually magenta. Okay, so there's all of the combinations that we can get on the faces of the cube. And here's the part that I put a lot of effort into doing this. I made the colors on the inside of it as well. So we can take this apart and we can see that each one of those combinations of red, green, and blue gives us a position on this, or in or on the faces of this cube. That's a concept that is going to be useful for us. What does the software have to do in order to get color separation to work? Simplistically, we can think of it this way. We start off with an RGB image, red, green, blue image that came from a camera, and we need to convert that into the printed version of it. And I think you'll notice that these color spaces are really just inverse of each other. So the software, essentially what it is doing is it's taking this combination of calculations here. Cyan is equal to 255 minus the red, and same with magenta and yellow. Fairly simple. This would kind of work. You wouldn't get real good color rendition, but that's the basic idea behind it. Theoretically, black isn't needed. I could get all of the colors if I just use cyan, magenta, and yellow. But why do we need more? First off, if I have a pure overprint of cyan, magenta, and yellow, theoretically it should be black, but just like the red doesn't turn out quite the shade that I want, and it's kind of an orangey red, and what was the other one? Green was nice, but the blue was kind of a purplish blue. Just, those aren't good. And also, if you add cyan, magenta, and yellow to try to get black, you actually get kind of a dark, muddy brown. So black will allow you to get black. Black ink, the addition of black ink, will allow you to get the color black. Another thing to consider is that I could make dark areas with a lot of cyan, magenta, and yellow, or I could just put down a layer of black. And black ink all by itself, one layer of black, is going to be cheaper than cyan, magenta, and yellow all combined together. They're both more expensive inks, slightly, and having 3 layers of it is kind of wasteful if you can get by with just putting black ink down. The third reason, and this is kind of a big one, especially if you have text, if you have magazines or ads that have text in them, if they don't register well, if it's out of register. Here we see the word hello that's printed with, theoretically printed with cyan, magenta, and yellow. We see that there's an edge on the top here that's cyan and an edge over here that's yellow. If our registration is off even by 1/1000th of an inch, which doesn't sound like a whole lot, just 1/1000th of an inch, it's going to be perhaps not noticeable, but annoying. It'll give you headaches, and just it won't look nice. It doesn't look nice and crisp. So I could print those with cyan, magenta, yellow. I could print text with those colors, but that's probably not such a good idea because of the misalignment that you're going to get on press naturally. Are you ready for myth number 5? Here we go. Myth number 5, yellow absorbs all of the blue light. We know that yellow ink will transmit red and green light, but what about the blue light? Does it absorb all of the blue light? Am I getting all of the blue light out of the system here? My camera is now looking at a sheet of paper, and I put the yellow acetate on top of it. Now I'm going to double that up. And what we see is that we've got a richer color. And if I triple it up, like this, we see where we have the overlap of all 3, it's a much darker, richer yellow. How do I explain that? The simple explanation is that filters are not perfect. Although we would like our yellow filter to take out all of the blue light, there's still some blue light left. It attenuates it, it does not eliminate it. So if I put down another filter, if I pass the light through 2 layers of that yellow filter, I get considerably less blue. So there is a change in color. Now, this is kind of important. This tells us that the amount of ink, this is like 1 thickness of yellow ink, and this is like 2 thicknesses of yellow ink. The amount of yellow ink is going to dictate the color that I get. I'm going to have to be careful on press to make sure that I get exactly the right amount of ink to get the right color that I want. That's an important consideration. I'm going to say that again because that is really important. The color that I get depends upon the amount of ink that I put on the page. The thicker the ink, the richer the color. But let's talk about beer. I have here a bunch of sophisticated equipment. We have a power supply here that is feeding an LED. That LED goes into a mixing tube, and there's a lens here. That lens is focusing the light from the LED over to here to this meter. This is a light meter, similar that you've seen these with cameras. So it's measuring the amount of light that goes through. Let's say I calibrate this thing so that with nothing in between, there's the lens, so the light is coming through here, and there we see the light sensor. Our light meter is calibrated now to give us 100 banana units of light. A banana unit is like, I'm not going to specify lumens or any lux or anything like that, foot candles. I'm just going to say banana units. Let's just say I add one beer in between. So the light is going from here, it goes through the beer, and then it gets measured on the other side. And I see that I get 90 banana units of light. So I've lost 10 banana units. Basically, 100 photons. A photon is a little tiny particle of light. 100 photons went to the bar, and 10 of them wound up drunk on the floor. The other 90 made it home that night. If these photons were to take another stop at another bar, have 2 beers instead of just, this by the way is a Roman ordering 5 beers. So if the photons were to go through a second layer of beer, how many do you think how many would come out? What will my meter read? What will the light meter read if I have a second beer? We start off with 100 with 0 beers. We have 90 with 1 beer. And then I add 1 more beer, and I would get, think about that for a while. If you said 81, you'd be correct. But some of you, I'm going to guess, said 80, because that would, make sense. You go from 100 to 90. The next one would be another 10 get lost. But no, you got to think of it in terms of the fact that the second beer is only going to have 90 photons going in. And if 10% of them were captured here, then 10% of that 90 are going to get captured in that second beer. So we're going to go from 90 down to, let's see, subtract 10% of that, subtract 9, that gives us 81. And obviously, everybody is thinking now, oh yeah, if I put a third one in, I'm going to get 72.9. I'm sure everybody thought of that. And the next one would be 65.61 or 51 or something like that. I do want to reassure everybody that no beer was wasted in this experiment. Oh, yeah. What kind of beer do you think I used? Oh, I'm so funny. There is a serious thing, a serious point underneath this. You now understand the Beer-Lambert-Bourget law of absorbance. You now would be able to calculate, given a layer of 1 thickness of ink, what the effect of 2 layers would be. It just happened to be a nice pun that August Beer was one of the 3 scientists that independently came up with this law. So let's actually go through that exercise. Let's say that we have a layer of paper. On top of that paper, we have 1 thickness of cyan ink. We hit this with red light because cyan is going to absorb the red light. It's not going to do much to the green and the blue light, so we'll look at the red light because that's the important part. And let's say that we just arbitrarily assign that to 100%. 100% of the light hits this. So we got 100 banana units of light. And let's just say that when it goes through, there's a little bit of red light absorbed. So let's say it's 50%. Half of the light that hits the surface is going to make it through to the paper. Now, some of it is going to reflect from the paper. It's not going to be perfectly reflective. So let's say we're down to 40%. That means that we've got 80% reflectance in the paper, which is, it's a little dark, but I want the numbers to be nice. So 40% of the light, 40% of the original light is going to be bouncing off of the paper. And it's going to go back through the cyan ink. And like before, 50% of it was absorbed. So now we're going to have, how much is going to come out? 20%. Half of that is going to come out. So here we see that we have a cyan ink. Each layer, each pass through it is going to absorb about half of the light. We're going to go through twice. And we're going to be left with about 20% reflectance. So the reflectance of one layer is equal to the transmittance, that's the 50%, how much transmitted through that ink, times the paper reflectance, times that transmittance again. So let's take a look at 2 layers of ink. We have 100% light, of red light, hitting the cyan ink again. 50% makes it through the first layer, which was actually the second layer, the second one applied, but through the top layer. 50% of that makes it through the bottom layer, so we have 25% that hits the paper. And let's see, we have 80% of that, so that 20% is left that's bouncing back through that lower layer of cyan ink. So we get 10%, and then it goes through that again, and we're left with 5% of ink. So 2 layers will give us a density of 1.3. So here we see the equation. When we have 2 layers, we have the transmittance squared, in other words, the 0.5 times 0.5, which would give us 0.25 times the paper reflectance times that transmittance squared again. And of course we can simplify that equation, the transmittance to the 4th power times the paper reflectance. This is Beer's law applied to multiple layers of ink film thickness. And for those of you who want to see a general equation here, we have the reflectance of the paper, which is on the left-hand side here, multiplied by the transmittance raised to the 2 times the thickness power. And here thickness doesn't have to be 1 or 2, it could be 1.6 or whatever. And that's times the reflectance of the paper. And we can plot that. We start off with the amount reflected by the paper, and it exponentially decays from there. So, unlike paint, one of the differences between paint and ink, the color depends upon how much ink that we put on the page. And that's the yin and the yang. That is the good and the bad. The good part, the nice part about this, the happy side of this, is that we have the ability on press to adjust the amount of ink that we're putting on the paper. And the bad part of that is that we have to adjust the amount of ink that we put on the paper. So here we see, this is the last page of my PowerPoint. This is on Canvas now, so you can go look at this. We have the book that I have discussed before, the RGB Color Theory book that describes all of this, maybe not in quite the detail. I have a couple of blog spots. Here we see what is the most accurate color wheel, DIY with RYB printing. This is the exercise that we had where we were testing out the different collections of primaries. And this last one is what we just went through. One Beer's Law too many. Have a good day.